Hi everyone, I'm going to work through an example problem from the textbook. This is an example of a system with more than one component. You can find this example as number 4.96 in the 7th edition of the textbook, and this problem includes a valve and a heat exchanger. This problem is asking us to find the pressure at state 2 and the mass flow rate of the bottom section of the heat exchanger, given the information shown. For this problem, we're going to start out by looking at the valve because we already have a lot of information about its current state. At state 1, we know the temperature, we know that it's a saturated liquid, and we were given the mass flow rate of the refrigerant. At state 2, we know the temperature, and we know that the mass flow rate is going to remain constant from state 1 to state 2. The other important thing we know is that it's a valve, which means that the enthalpy is going to remain constant. So once we find the enthalpy at state 1, we will know that H1 will be equal to H2. If you didn't remember that enthalpy remains constant in a valve, you can always figure this out by doing the first law for an open system, and you can do your energy balance to calculate it. You can always go back and look at the textbook or look at the review video for system components to figure out how we got that. Now we're going to go to our tables to pull properties at states 1 and 2. And so for this one, we are looking at refrigerant 134A, which means we're going to need table A10. At state 1, we are at the temperature is 36 degrees Celsius, and we know that it's a saturated liquid, which means that we will be pulling the value for HF. And so that means that our value of H1 is going to be 100.25 kilojoules per kilogram. We also know that at state 2, the temperature is negative 8 degrees Celsius. And so for this one, we're going to pull the pressure in bar, and we're also going to pull the HF and HG values. So now that we have the values that we're pulling from that table, we're going to use the values from table A10 to help us answer the question. So we have that at T equals 36 degrees, we got the value for H1, which was the enthalpy at the saturated liquid point for that temperature, which was 100.25 kilojoules per kilogram. We also know that the enthalpy at state 2 is going to equal the enthalpy at state 1, and so we can write that down as well. We also learned from that table that at the temperature of negative 8 degrees Celsius, we could get the pressure, and that is one of the things that it asked for in this problem. It asked for P2. So at T equals negative 8 degrees Celsius, which is state 2, we got that the saturation pressure is 2.1704 bar. So we also got that at that temperature, HF was equal to 39.54 kilojoules per kilogram, and Hg was equal to 242.54 kilojoules per kilogram. So we know that the pressure at state 2 is equal to the saturation pressure at that temperature because the enthalpy value that we got at state 2, which was 100 kilojoules per kilogram, that is in between your HF and HG values, which were 39 and 242. So you know that this point is going to be under the vapor dome, so the pressure will just be equal to the saturation pressure at T equals negative 8. So that means we know that P2 is going to be equal to 2.1704 bar. Or, because it asks for it in kilopascals, it's going to be equal to 217.04 kPa. Now that we're finished with our valve and have the values at state 2, we can begin looking at our heat exchanger. Let's start by getting the values for state 3. At state 3, we know that it's a saturated vapor and that the pressure at state 3 is equal to the pressure at state 2. Because in the previous step we used table A10 to grab the pressure at state 2, we know that P3 is going to also be equal to 2.17 bar. Because we know that it's a saturated vapor at that pressure, our value for H3 is just going to be equal to the Hg value at that pressure. So we have that our H3 value is going to equal 242.54 kilojoules per kilogram. So part B of this problem is asking us to find the mass flow rate in the bottom stream of the heat exchanger. So we're going to use an open system energy balance so that we can find an expression for this mass flow rate. We know that the system's at steady state. If we draw it so that our system is the entire heat exchanger, including both streams, then all of the heat transfer that's occurring is internal to the system. There isn't going to be any heat transfer crossing the boundary of the system in or out, and so because of that, we can neglect our Q. There's no work being done to the system, and there's no significant change in velocity or elevation, which means that our kinetic and potential energy changes can also be neglected. This is going to leave us with 0 equals the sum of the mass flow rates in times their enthalpies, so that's going to be m dot 2 H2 plus m dot 4 H4. And then we're going to subtract the masses leaving. So that's going to be m dot 3 H3 minus m dot 5 H5. We know that the mass flows at 2 and 3 are equal, and 4 and 5 are equal. So because of that, we're going to have that m2 times H2 minus H3 plus m dot 4 times H4 minus H5 will equal 0. And then our final expression for m dot 4 is going to equal m dot 2 times H3 minus H2 over H4 minus H5. And this is going to be the expression that we'll use to solve for the mass flow rate. We already know H2 and H3 from the previous steps of the problem, so now all we need to do is find H4 and H5, and then we'll be set. So now we're going to go back to our tables to get the approximate values for enthalpy at states 4 and 5. And so because these are liquid water, we're going to use a compressed liquid approximation at the temperatures, which are T equals 20 degrees Celsius and 10 degrees Celsius. From there, we're just going to grab the saturated liquid enthalpies at those two temperatures, and those values are going to be the approximate values for H4 and H5. And now that we have all of our enthalpy values, we can plug into the expression that we got from our energy balance to solve for the mass flow rate at the bottom of the heat exchanger. So we have that the mass flow rate at 4 is going to be equal to the mass flow rate at 2, which is 0.26 kilograms per second. And then we can multiply that by the differences in our enthalpies. So we know that our H3 is equal to 242.54 kilograms or kilojoules per kilogram. And then we're going to subtract H2, which is 100.25 kilojoules per kilogram, divided by our new values for H4 and H5, which are going to be 83.96 minus 42.01. And that's going to give us our final value for the mass flow at the bottom of 0.882 kilograms per second. And that is the final answer for part B of this problem.